In the last video, we showed that every field was an integral domain, but then we considered the converse of that statement, namely, is every integral domain a field? And by counterexample with the integers, we saw that we can have an integral domain, but it does not have to be a field. For example, the integers are not a field because the only non-zero units are 1 and -1, but in the field, every non-zero element has to be a unit. However, in the following theorem, we get a nice result, which tells us that if we take an integral domain and we require it to be finite, then that ring is a field. So let's prove this. Since R is finite, that means it's got a finite number of elements. So let's call these elements A1 through AN. And so what we're going to do is we're going to take any non-zero element, so let's call that A sub t. So suppose that A sub t is not equal to 0. And we want to now take this A sub t and multiply it by every element in our ring. So consider the products. A sub 1 times A sub t, A sub 2 times A sub t, A sub 3 times A sub t, all the way up to A sub n times A sub t. Well, since we multiplied A sub t by n elements, we're going to get n products. And so what does it mean if two of these things are equal? So if A sub I, A sub t equals A sub j, A sub t, because this is an integral domain, by cancellation, this implies that A sub I equals A sub j. So basically, if we have that two of these products are the same, it means that we multiplied A sub t by the same element. But we're multiplying each A sub t by the distinct elements of our ring. So it follows that A sub t, that should be a subscript, times A sub I for some I is not equal to A sub t times A sub j if A sub I is not equal to A sub j. So what does this tell us? It tells us that we've got n distinct elements in our ring and we have n distinct products. So these products represent the elements of R. Now they may be in a different order, and that's okay. But the point is, if we take a non-zero element and multiply it by every element in our ring, we're just going to get every element in our ring back. It's just going to be in a different order. These products are all going to equal other elements in the ring, and we're going to get n of them for the n elements that we started with. Now, in particular, because it's an integral domain, it's a commutative ring with identity. So there is an identity element. And so one of these products has to equal that identity element. So in particular, for some j, A sub j times A sub t has to be 1. Well, what does that mean? So A sub t has a multiplicative inverse. This means that it's a unit. But A sub t was arbitrary, and we could pick A sub t we could go through every single element of the ring and get this result, except for the 0 element. And so we've shown that R is a field.